Starting from this lecture, we are going to talk about vectors. First, we are going to extend our rectangular coordinate plane into a three-dimensional system. Just like the xy plane, which is you have two coordinates. Each coordinate could be any real number, right? In a three-dimensional space, we have three letters, three variables, x, y, and z. Each of them could be any real number. So we use this R, but sort of have a extra stroke. This is like a math R, to denote the set of real number. And since you have a real line for x, and then you have a real line for y, and then you have a real line for z. That's why you have three R's. When you put them together, we write it as R3, like R times R times R equals R to the third power. Okay. So R3 is a three-dimensional space, and every point or every element in this set looks like three coordinates x, y, and z. In each of them could be any real number. Okay, then this set of ordered triples of real numbers is denoted by R3, and like our R2, there is a one-to-one correspondence between the points in the space, three-dimensional, and ordered triples in R3, which means if you have a point in the space, after you set up this coordinate plane, after you set up where the origin is, where x, y, z axes are, what the scale on each of the axes is, you point any point in the space is corresponding to one triple. And also, if you come up with a triple, three numbers for A, B, and C, for X, Y, and Z, then you can find the point corresponds to it. And because we are having three-dimensional, we used to set up our X and Y axes as X point to the right and the Y point to the up, and they meet at the origin. What do we do with the third coordinate? What do we do with the third axis? We follow this right-hand rule, okay? Which means when you do use your right hand to do a position of thumb up, like you can see here in the picture, naturally your thumb is pointing upward and your other four fingers is making a loop. So the direction your other four fingers is making, that is the direction you want to go from your x-axis to y-axis with a 90-degree angle. Because here if you want to go to your in the space in the coordinate plane that I drew, if I want to go from the positive direction of x-axis to positive direction of y-axis, I can go this way. I also can go this way, but this is the shorter way, 90 degree. This is the longer way, 270 degree, right? So we go with the 90 degree. That means not the 270. Yeah, so we go this way, which means you are going to place if you hold your thumb up with your right hand, you are supposed to put your hand right on top of my screen, and your thumb will be pointing out of the screen. That is the positive direction of your Z axis. Of course, you are drawing a three-dimensional thing in a two-dimensional object, which is the paper over here, my screen. It's not really possible, so we can really illustrate it. although in the textbook, the way they did it is x always go pointing to the lower left, y pointing to the lower right, and then z goes upward. Personally, I like to set it up a little bit different, not a lot of difference. The only difference is I still prefer, and actually I feel like most of the people prefer a horizontal and a vertical axis. So anyway, it's an illustration, so you can do what the textbook does, but I like to draw my y-axis horizontal, pointing to the right. So this is how I set up my plane. Well, sorry, my space. You pick the origin, your x goes to lower left, and the y go direct to the right. And then this is supposed to be 90 degrees, but since you are sort of looking at it above the plane, so it doesn't really appear like a 90 degree. You need to understand it's a 90 degree and use the right thumb rule. The z will be pointing upward. That's z, o, x, and y. Okay, that's how I set up the plane. Now, how do you sketch all these points? Sort of the same thing. You go to the x-axis, find the x coordinate, then you move to the right. As what the y coordinate is, well, if it's positive, or move to the left. If it's negative, then you end up with wherever it is, then you move upward or downward depending on the z coordinate. And this picture is to show you that. For your ABC, you start from the origin, you go to the point A on your x-axis, then you go B, do B based on what y coordinate is, then C will be moving upward or downward. Again, it's an illustration. You are drawing a three-dimensional thing in two-dimensional, so sometimes it's a little bit confusing when you see the picture. Okay, now let's try example 1. Sketch the points. Okay, so here I have 4 points and I want you to do it on a single set of coordinate planes. So maybe I'll remove my axis and make it bigger. So let me use thinner. So this is the origin, this is my x-axis, and this is my y-axis, and this is my z-axis. X, Y, Z, and the origin. First point, well, let me set up the unit. So on my x-axis, I need at most 3 for positive or negative. So this is the Y and this is the Z. Okay, so this is 1, 2, 3. 1, 2, 3. 1, 2, 3. I didn't draw the negative side. We will when we need it. The first one, we start from x equals 2 here. Then y equals 3. I go to the right by 3 units. So I go this much long to the right. Well, the thing is that although it's supposed to be a rectangle, because of, again, you are illustrating it, what you will see is a parallelogram. So instead of, if you don't have a scale to measure, the same length as from the origin to 3, the 3 units to the right, if you can't do that from the point 2 on the x-axis to here right away, you can make a little parallelogram from x equals 2 and y equals 3, and then they will meet somewhere, and that's your point. Okay. So it will be here. You go 3 units, it's here. Let me again use dotted line. Okay, so they will meet somewhere. That's my 2 and 3. Now negative 1, starting from that point, I go downward 1 unit. So this point is my first point, 2, 3, -1. The second point is 0. So I start here, 3, I get here. I go along y, I go to 3, then -1. So this time I go downward from here, also 1 unit. This is my 0, 3, -1. Now if you see I complete this, this will be like a box. Okay, but of course I don't want to have all that. Just letting you see actually these 2 points are both like 1 unit below the xy plane. The 2 points we drew. If you imagine the xy plane is the ground, then both of them are like underground but with same distance. Okay, the third point we have 0, -3. X equals 0 is the origin, y equals -3. So this time I am going to extend my y-axis to the negative side, and then I have my unit 1, 2, -3. So x equals 0, y equals -3, and z is 1. So I go upward 1 unit. I'm here. This is my 0, -3, 1. And finally, I'm having 0, -3, 0, which will be here. 0, -3, 0. So again, if you are thinking xy plane as the ground, then only the 0, -3, 0 is on the ground. 0, -3, 1 is above the ground, and 2, 3, -1 and 0, 3, -1 are below the ground. Okay, so there are layers. Okay, I hope you sort of see a little bit, like the thing become 3-dimensional. It takes a lot of imagination. In the beginning, it's always kind of hard to imagine, how things go in a 3-dimensional space, especially when we see them and we have to imagine instead of really seeing a 3-dimensional object. Okay, anyway, that's how you plot points. You go to x-axis, find the x-coordinate, then you move left to right depending on the y-coordinate, then you move up or down depending on the z-coordinate. Next, we are going to sketch these planes. These equations are all planes. You are in a 3-dimensional space, and when you have a sort of linear equation, you lose 1 dimension. So you are getting 2-dimensional objects, which are, in this particular case, since they are all linear, you will end up with plane instead of curvy surfaces. Anyway, so x equals 2. I set up my x, well, let me use purple, x, y, z plane. My z is a little bit too, okay, that's a little bit better. X, y, z. And x equals 2. So I go to my x equals 2. And from there, I can go anywhere to the left, to the right, up or down. That will be my space. So the space will be parallel to the YZ plane. In order to make that more visible, you draw the space with a parallelogram where the sides of the parallelogram are parallel to the axes, okay, of the parallel axis. So the x, I don't know if I make it clear, but this is the deal. Your x equals 2 is parallel to the plane that has y and z axes. So you are going to make a parallelogram, in this particular case, a rectangle containing the point. But it's so hard to do it on an iPad. Okay, so you're using parallelogram where two sides are parallel to the y-axis and the other two sides are parallel to the z-axis, because this plane is parallel to the yz plane. Actually, if you look at the textbook, what they did is, now let me use red, they sort of show what you still can see by making them solid. They actually, this part you can see, make the things behind the plane dotted, and then they also shade the plane a little bit like this. I don't know if it makes it better. I think it does a little bit, but of course with pencil or maybe the best pen, it's very hard to do it. So I don't really ask you to tell what is seen, what is before or out of the space, like the space doesn't cover it, and what is covered by the space. You don't need to do the behind this the plane thing, or in front of the plane thing. So you don't need to do any of that. But of course I need to say this is 1, this is 2. Okay, so if you want to, a little bit of shading might be helpful, to sort of make the plane, which in this case the rectangle stand out a little bit more. Now the second question, z equals -1. So I don't really have any information about x and y, but I do know z equals -1. So I go to my z-axis, I find -1, I make a dot. That's -1 on z, and then you draw a plane that is parallel to, since you're on z, the plane will be parallel to the xy plane, which has x and y axis. So that's the plane, and then you shade it a little bit. Okay, that's the plane. The third one, x equals y. So first you need to find x equal to y. Maybe in xy plane. In xy plane, 0 and 0 makes x equal y. Also 1 and 1, which will be here, makes x equal y. 2 and 2, which will be here, also makes x equal to y. So actually x equals y is a straight line in your xy plane that looks like this, passing through all the points with 1, 1, 2, 2, 3, 3, or -1, -1. Then you have no control on z. Z can be anything. So instead of drawing a point, right, and drawing a parallelogram that passing through a point, you want to draw a parallelogram containing this line. So this line will be like the boundary, not the boundary, but like parallel to the boundary, and also the other boundary will be the z. That's like the other dimension. So we make it a little bit up and down, and then we draw a parallel line to our x equals y. I need to go a little bit further. Yeah, that's better. And I also go up a little bit and draw a line parallel to it. So then this is, oops. Okay, that's the plane. I like playing with sharp corners. That looks better. Okay, so that's the origin, and this is really 1, 1, 0, 2, 2, 0. Those are the points that I'm drawing. And that's the plane. Well, again, I know this part is a little bit hard. You need to take a lot of imagination, and even you are seeing the pictures that I drew, I don't know if you can really make them as what they are. Like x equals 2 is like a wall standing right in front of you, and z equals -1 is like a parallel layer but like be under xy plane, and x equals y is really like I don't even know how to say it. It's like a sideways wall standing above the ground and below the ground, actually. So that's the planes that we're drawing. Next, we have the distance formula. Again, the whole thing is an extension of what we already knew in the plane. When we have three-dimensional, you just need to take care of the third dimension. So the distance formula when we were in two-dimensional is the distance between 2 points are square root of x2 minus x1 squared plus y2 minus y1 squared. Now, having the third dimension, you just add the difference between the z coordinates and square it. That's our formula. And let's try the example 3. Find the distance between the 2 points. Let me take away that formula first. So the distance, I'll denote as d, is square root of difference in x coordinate squared plus difference in y coordinate squared plus difference in z coordinate squared. And that is 2 squared plus 6 squared plus -2 squared. And that is 4 plus 36 plus 4, and that's 44. Simplify it, square root of 4, which is a perfect square. That's why we factored it out, and it becomes 2 square root of 11. Before I send you to try the practice number 1 through 3, here's a remark. Since we know the distance formula, then we can do a sphere, like a ball in the space with any center. So pretty much all the points on the sphere has the same distance r to the center. So the equation of the sphere will just be all the points that the distance to center equals r, where you square both hand sides, it will be the sum of the squares equal to r squared. Again, compared to the circle in R2, we have x minus x0 squared plus y minus y0 squared equals r squared. Again, you just have one more dimensional, z minus z0 squared. Okay, now you can try practice 1 through 3. Here we are going to start the vectors. So a vector is actually, for me, vector is like a path or a way of going. So a vector is often represented by an arrow or a directed line segment. The length of the arrow represents the magnitude of the vector, and the arrow points in the direction of the vector. So, a vector is how you go straight from one point to another. You have to go this far, and you have to go along this direction. The length and the angle. That's a vector. Okay? And they are straight. You can't do... So this is A, this is B. Let me use another color. They were pink. This is A, this is B. You can't do funny stuff like this. That won't be a vector. You have to go straight there. And the vector is just the line. If you draw the vector, it will just be the line segment go from A to B with an arrow ending at B. we denote a vector by putting an arrow above the letter V or by printing a letter in boldface. Actually, in the textbook, you will see vectors like that, okay? A darker V, which you apparently you can't do when you are writing. So I try my best to write all my vectors as the handwritten way with an arrow on top. So vector V. Okay, or here, like my first vector, is the vector goes from A to B with initial point A and the terminal point P. And we can say the vector V is the vector goes from A to B. Now if you look at the two vectors together, I have a vector V goes from A to B. I also have another vector U goes from C to D. They are not the same vector in the sense they look different, but they both have the same length and they go to the same direction, parallel direction. Okay, so if you set up the plane, this will be same angle. That makes them same direction. They're parallel. Okay, for that reason, we say that vector U and vector V are equivalent if they have the same length and the same direction. Then we have the zero vector, which is denoted by arrow 0, which is a vector starting from a point, then you go length 0, which means you don't go anywhere. You stay there. And since you're not moving, you have no direction. And zero vector actually is the only vector that has no direction. Just like number 0 is the only number has no sign. Because in a way, on one-dimensional space are, negative and positive are directions. So that's our vectors. Now we can talk about the operations of vectors. First, how do we add to vector? Well, again, vectors are, to me, are like paths. You go from A to B directly. Now, if you're adding two vectors, pretty much you go from A to B, then you go from B to C. That's how you add vectors. And here, addition, if U and V are vectors positioned so that the initial point of V is at the terminal point of U, then the sum is the vector from the initial point U to the terminal point of V, which is called the triangle law. What does it mean? So I'll follow the picture I drew. So U looks this way, and that's a little bit too much. This is V. I think U is a little bit longer. Then U plus V will be, I put a V. U goes from here to here, and then I put a V. The initial side of V at the terminal, initial point of V at the terminal point of U. So I go along U, then I do V. Then what did I do? Actually, I went from this point to this point. That's my V. Okay, U and V. Then what I actually do is from this point to this point. That's my U plus V. And this is the triangle law, which means U plus V, you just put U there and then you put V on the other side. You connect the third side. That's your triangle. And the third side is the sum. Vector addition is commutative, which means you go U first, V second, or you go V first, second, U second. Doesn't really matter. If you go V first, U second, it will look this way. But if you look at this is V, this is U, the result, this is V plus U. They are actually the same in the sense they are same length, same direction, because here. If you sort of move this triangle here, you will have a parallelogram. They are actually the same, and it's shown in that picture I circled. So as all the additions, we have commutative law, which is nice. Now scalar multiplication. A scalar multiplication is when we multiply the vector by a number. You double the vector, you go the vector twice. That's what you want to do. You have the vector, you want to go half of the vector. So the scalar multiplication is only on the length. Okay, so you multiply, you change the length, but you don't change the direction when you multiply by a positive number, and when you multiply by a negative number, you reverse the direction. And if you're multiplying a 0, this part I should type up the arrow here, where V is the 0 vector, then the multiplication gives you the 0 vector. And what that means is that 0 multiplied by 0 gives you 0. No matter the 0 is the number or the vector. Because 0 vector has 0 length. As long as the length is 0, the direction doesn't matter anymore. After we have multiplication by negative numbers, we have negative, which make it a subtraction. So when we do u minus v, we're just doing u plus negative v. Go back to our u and v again. So my u look like this, my v look like this, right? And well, I think the v is a little bit longer. If v is that way, negative v will be same length, reverse direction. Then u minus v will just be u, then v. So this will be u minus v. You go u, then you go negative v. And sorry, that is a negative v. That's how to do subtraction. You reverse the direction of the vector. Example 4. Now we go back to R2, which is easy to graph. So I give you 2 points, 2, 1, and negative 1, 2. And of course, the origin is 0, 0. So first, we are going to plot A and B. Easy, right? We have xy plane. Here's x, here's y, here's 0, and I give some scale. I only need 2, so positive and negative 2 on each of the axes, and then I have, do I want to mark them? I can. Negative 1, negative 2, 1, 2. A will be 2, 1, which is here. Use another color. That's A. And B is negative 1, 2, which is here. B. And O is 0, 0, of course, which I didn't ask you to plot. Okay, so that's my A and B. Now graph the vectors. Vector A is OA and vector B is OB. So actually you are going to do exactly the same thing. Well, that's not very good scaling. That's better. X, Y, 0. I'm looking at my A is 2, 1. That's my A here and my B here. Now vector A is the arrow goes from O to A. That's vector A. Vector B is from O to B. That's my vector B. Okay, that's my vector A and B. Next, we are going to graph more complicated stuff. Graph vector A minus 2B. So let me first give you the A and B back. 1, 2, 1, 2. Oh, a little bit nicer since we're doing very careful graphing here. 1, 2, 1, 2. So my A is this. That's my A, and my B is this. That's my vector A and B. Origin X and Y. Now if I do A minus 2B, I do A first and I do negative 2B, right? So first, negative 2B is pretty much you double the B. That's 2B from here, from the origin. That's 2B, then you reverse it. So if you really look at what B does, you go to the left 1 unit, you go up 2 units. So reverse it, you go down 2 units, you go to the right 1 unit. Twice it, you go. So when you are, let me just do it on the side, that's better. So if you look at what happened on that, negative 2B, you pretty much, well, maybe I'll do it outside my graphing. So negative 2B, what happens is you go downward 4 units. And you go to the right 2 units. So A then 2B, you will go downward 4 units. You go from 1 to negative 3, and meanwhile you go to the right 2 more. So that's your negative 2B. And then you connect the A and then the negative 2B. The initial point of A is the origin, and the terminal point of the negative 2B. And put them together, that's your, do I do purple? I'll do red. So here, this is my A minus 2B vector. Actually, the terminal point is, remember you went to the right 2. This is 2, 1. Then you went down 4 units and to the right 2 units. So this is for negative 3 as the terminal point. But the vector we are really getting is the origin 2, 4, negative 3. Okay, and you get it by, you need to show the vector A, then the negative 2B, and the sum, the triangle. Last example for today, we are graphing, instead of calling them A, B, I'm calling them AO and BO. So 1, 2, 1, 2, 1, 2, 1, 2. So AO will be backward from A to O. So that's my AO, and here from B to O, that's my BO. Then AO plus BO. You finish your AO, then you move an equivalent vector as BO at the starting at the origin. So you do another one like this, and the path will be, use another color. The path will be AO then BO. So overall, at the end you get this. That's AO plus BO. Without really writing out, really calling them little a and little b, you can still use, the endpoints to denote the vectors. Okay, that's it for this lecture. It's a lot of graphing and you need a lot of imagining, but I think it's not hard, it just takes some time to get used to. Okay, now you can finish the practice 4 through 6.